Astronomy is one of our oldest sciences, and as technology progresses, our capacity to observe, study, and learn from the cosmos expands exponentially. One of the most recent achievements has been the discovery of exoplanets and the deployment of cutting-edge telescopes to detect even more. And these telescopes were successful, finding thousands of exoplanets over the years, of all sizes, and orbiting at sometimes surprising distances from their star. I'm thinking of a few systems that were observed to have huge gas giants orbiting rapidly right up close to the star. While that kind of stuff is new and pretty interesting, it's not what I want to talk about today. Today, I want to talk about a recent study from Harvard that analyzed Kepler exoplanet data to organize these discovered exoplanets into groups based on their radius and their presumable composition. Before I dive into their results, I should first explain a little bit about the astronomical science that's involved here. When we detect exoplanets, there's a small handful of variables that we can calculate to get a rough idea of what that planet might be like. Most obviously, we can see how far it is from its host star, so we can get an approximate idea of how much light and heat it might be receiving. We can also see when it orbits the star by measuring the flickers in the star's luminosity, and this can tell us both the speed and the distance at which the planet orbits, as well as the physical size of the planet itself. By measuring the wobble that the planet's gravity induces on its star, we can calculate the planet's mass. Spectroscopic analysis can give clues as to the chemical composition of the planet's atmosphere. Once we have all of this preliminary data, we can find relationships between the variables and pick out patterns. For example, if a planet is observed to be small and dense, it's presumably a rocky terrestrial planet like Mars or Mercury or the Earth. If a planet is really large, like its radius is more than 10 times the radius of Earth, then physically, structurally, it has to be a gas giant, like Jupiter, Saturn, or Neptune. Purely terrestrial planets can't get this big, because the gravity would either crush the planet and make it smaller, or the planet would just be physically unstable and it would fling apart into smaller pieces. If a planet is slightly larger than the Earth, but it has a weirdly low mass, then it's quite likely that the planet that we're looking at is a water world. A huge portion of its radius is ocean, and this massive global ocean, it'll add to the planet's radius, but it'll possess less mass than an equal volume of rock. And now we get to the study in question. In this study, the researchers calculated that rocky terrestrial planets were those with a radius, at most, twice that of Earth. Planets that have a radius between 2 and 4 Earth radii were determined to be water worlds, with super deep, presumably global oceans. If a planet had a radius larger than 10 Earth radii, these planets were so large they could only be gas giants. And lastly, exoplanets that were between 4 and 10 Earth radii were called transitional planets, as they formed a transitional range between the smaller, rockier, watery worlds and the larger gas giants. Interestingly, this transitional range has a relative lack of planets. I should clarify that these are general rules of thumb. These are general trends that the researchers started to notice when they were analyzing all of this exoplanet data. But it's not as if I'm explaining the full nuance. These things aren't absolutes. There's always exceptions to the trends. For example, there are gas giants that can be as small as around 2.5 to 3 Earth radii. So you might think that they should be water worlds, but the evidence suggests that they're presumably gas giants, like mini Neptunes. In any case, the researchers found from their analysis that up to 35% of the known exoplanets could be water worlds, which has some really big implications for potential alien life. Li Zheng is the lead author of the study, and while talking about all of these water worlds and potential alien life, he said, quote, "Life could develop in certain near-surface layers on these water worlds when the pressure, temperature, and chemical conditions are appropriate. One has to realize that although water appears to be precious and rarer on Earth and other inner solar system terrestrial planets, it is in fact one of the most abundant substances in the universe, since oxygen is the third most abundant element after hydrogen and helium." Unquote. Here on planet Earth, the conditions are quite appropriate for life. We have a stable climate with good temperature and pressure that can support liquid water, and this liquid water forms oceans that are deep enough to create a wide range of ecosystems. You have the bottom feeders and scavengers on the sea floor, and then you have the open water, and then you have coastal regions with reefs and shallower areas where the seafloor is illuminated by the sunlight, and so marine vegetation can grow here. Presumably, on any other water world that still had some dry landmass, this would also be the case. If any dry land is able to erupt through the surface of the water, that would inherently imply that there's also regions of shallow water surrounding the dry landmass. These regions of shallow water could host alien vegetation, and this would serve as the basis of a more complex ecosystem, with possible heterotrophs, like alien fish. It would also mean that there were some regions of the ocean floor where mineral exchange and geochemical cycles can take place. And this is really, really important for life. This brings me to a subtle but devastating detail about the potential for alien life in a water world. Any water world that has dry land, even if it's just a few tiny islands, will not have that much water, relatively speaking. These would be the planets within the 1 to 2.5 Earth radii zone. But on water worlds that are larger than this, you would necessarily need so much water that all of the rocky land would be completely submerged. This isn't inherently prohibitive of complex life. As we can see from the natural history of life on Earth, the ocean teemed with complex life before there was ever anything serious going on dry land. So a water world with super deep global oceans could presumably still host a complex ecosystem with alien fish and alien vegetation and whatever else. But the devastating detail begins to apply when you start to look at the largest water worlds. These larger watery planets would be covered in global oceans that are so deep, hundreds of kilometers deep, that the pressure near the bottom of these oceans would be high enough to turn that liquid water into ice. If this kind of pressure exists across the entire terrestrial surface, if it exists across the entire ocean floor, then that means that there's going to be a shell of pressure-formed ice encasing the mineral bedrock of the planet. This ice layer would block off mineral cycling, as the liquid water wouldn't be able to erode and then absorb and mix mineral nutrients like it does on Earth. This geochemical cycling would be completely shut down, thanks to the impenetrable shield of pressure-formed ice. Without this geochemical nutrient cycling, you're not going to have enough mineral ions in the water to support complex life, or complex ecosystems. Maybe some microbes could theoretically exist, but the idea of these super deep water worlds being home to alien fish is pretty much impossible. Now, this isn't an absolute, because there are some variables that might tinker with this equation. For example, we know that the Earth picks up mass as it travels through space. Asteroids, dust clouds, all of this stuff rains matter down on Earth, and the Earth grows in mass. There's no reason to think that this wouldn't be the case for a large water world. It too would pick up asteroids and dust from outer space, and it would gain mass. This rocky material, whether it be asteroids or dust, would sink to the bottom of the ocean, and while it's falling through these hundreds of kilometers of water, it's quite likely that it could be picked up by some kind of aquatic microbe or aquatic organism. But if these mineral nutrients make it to the bottom of the seafloor, where they come into contact with the pressure-formed ice, then they're going to be lost forever as far as the ecosystem is concerned. This is because ice crystals form around a non-ice nucleus. Ice crystals form around little particles like sediment or minerals or debris, whatever. They have to form around some particle. And so if there's these mineral particles raining down from the ocean and landing on this pressure-formed ice, the ice is just going to grow around the particles and entomb them. Unless that ice gets melted, those particles aren't going anywhere. Now, in another circumstance, the planet might be geologically active, and so you might have undersea volcanoes and hydrothermal geysers and stuff like that. What would happen here is that if the ice layer was too thick for this heat to break through, then the ice closest to the volcano or the geyser, that ice would melt, and you would see the formation of this internal sub-ice ocean. So we have an ocean, a layer of ice, and then another warmer, higher salinity ocean underneath. It's theoretically possible that chemotrophic microbial life could thrive in these dark, high salinity sub-ice oceans, but we'll never really know until we can go there and explore. And exploring hundreds of kilometers under the ocean, where the pressure is so great it turns liquid water into ice, and then drilling below that ice, which would be another dozens of kilometers, just to get to this extremely low-depth, high salinity ocean, it just seems impractical, and it seems a little unethical to go through all of the labor to get down there just to potentially contaminate it, while you're ironically searching for endemic alien life there. There's also the idea that these undersea volcanoes and deep-sea hydrothermal geysers would melt through this pressure-formed ice. I'm a little skeptical of this idea because they're not going to be able to move the water out of the water column so as to make the pressure decrease, so the only realistic scenario I could see here for this undersea volcano breaking through the layer of pressure-formed ice to feed mineral nutrients into this giant global ocean, the only way that I could see that ever happening is if that undersea volcano was so hot, and I mean extremely hot, that it forced the phase change of that pressure-formed ice back into a liquid. And that kind of heat, I would imagine, I'm not sure if it's realistic for a deep-sea volcano to generate that much heat, but I suppose it could theoretically happen. I don't know. Maybe a geologist will want to chime in and give me his educated thoughts on the matter. But either way, you can see that this is kind of a wild duality to the cosmos. You have these smaller water worlds, which could be thriving oases of life. They could have a higher density of life than any other kind of planet in the cosmos. But if these water worlds get just a little too big, if there's just a little too much water on them, then the physics of super high pressure water leads to an ice shell that will prohibit the formation of complex life entirely. So smaller water worlds will be thriving with life, while larger water worlds would have massive oceans with incomprehensible expanses of open water, and they would all be empty, save for maybe a few microbes. If this study is accurate, with its estimate that 35% of the known exoplanets are water worlds, well, that's a lot of planets. So there's always a chance to see something that you don't expect. There's always a chance to be surprised. And I think that generally holds true for all life in the cosmos.